So today's objective is basically to understand why we require a design pattern in MapReduce, right? What is the use of a design pattern in MapReduce? Why we require a design pattern in MapReduce, and why MapReduce design pattern is very much important. So basically, before even starting, so general question is why design pattern, right? So what is the need to have something called as design patterns? Why basically design patterns are most important, not only in MapReduce, generally it's not only in MapReduce, so in across all the technologies like Java, maybe a .NET or maybe any framework across, right? Basically, when you look back into see it, design patterns are the first heavily considered in any coding, correct? So let's consider, for example, I want to reuse the code very much efficiently. I might have written some section of the code, and for one particular use case, I might have written a code and I'll get another use case. So here we have to see how smartly we can reuse the same code which is already existing, right? So that's where your basically design patterns is going to come up. So the intent of design patterns is to make the code easier to understand and also to make the code shareable across different use cases so that the reusability can be achieved to a greater extent. So that's what basically the target of design patterns, right? And why design patterns in MapReduce? So primarily because whenever you use a MapReduce, right? Whenever you use any MapReduce technique. So for example, I'll take a very simple way of telling you how much effectively design pattern can work in MapReduce. So let's take, I want to join between two files. Okay. Let's take, I want to join between two files. So let me take up a small notepad so that we can understand it. So let me say I want to basically join between two files. Whereas one file is basically having something around 1 million of records, and maybe another thing is going to have something around 20 billion of records, right? Okay. So if you consider this, the thing what is going to happen is not all the records is going to join. Some of the records might join, some of the records may not join. So the point what we want to do here, so when the map process happens, what basically a map process does, a map process basically takes all the records and shuffles, sorts across everything, then finally it goes to the reduce, right? In reduce basically we will take all the records which is coming up, again grouping by key, etc., all those kind of things. So here definitely we are sure that on the max the correct records can be only 1 million, because on the left hand side we have only 1 million, whereas on the right hand side we have 20 billion of records. So how can we make this very much effective? So why can't we filter some records smartly in the mapper itself? Why can't we filter records in such a way while going to the reducer, instead of sending all the records, we are going to send only certain amount of records. These are the things that design pattern is going to help you, right? So without design pattern, what happens? You basically take some certain amount of records and you will compare with another certain amount of records. Mapper is not effectively used. So that's what basically MapReduce does. In any MapReduce process you take, a basic thing in any MapReduce process, we just use mapper as a stream of communication. We just take something like a delimiter or take some this column and add this column. We just use mapper as something which is passing the records to the reducer in one formatted way. And reducer is basically getting overburdened. So if can we use the mapper smartly? So in this scenario, why can't I filter the records which is only matching and sending only a less amount of records to the reducer? Can I apply some filtering functionality there? Right. So this is a valid thing. Not only on this, let's take another scenario where you want to find some elements in a particular set, and the set might be having something like 1,000 records or 5,000 records, and you want to find an element. Before even finding the element, can a filter come up and say the element which you are trying to find is available here or not? Okay. If the element is not there, then we no need to search only, right? Then why I need to search? Tell me approximately whether this element will be available or not. Right? So these are some of the design patterns. If you apply these design patterns, so basically what's going to happen is that your records, etc., author things. As I said, this is one of the smartest use case where the mapper can be used very much effectively, right? So like this we can keep speaking on lot of things, not only on this, right? So let's like this, we are going to take one of the use case today, and we are also going to see how much effectively a filter can be applied on the same, right? So that's what basically we are trying to do. Okay, so let's take a MapReduce and let's see how it's going to work with the help of MapReduce. Okay, fine. So I'll just take one question. Deepak is asking, I'm not very much aware about MapReduce. Okay, Deepak, see, this particular thing is basically, to be really frank, it's targeting the problem in the MapReduce and trying to say if this design pattern has been applied on top of MapReduce, how much easily it can solve. But telling that you can also understand what is going in this session, because MapReduce is just an algorithm which is going to group the records key and value, right? We are not going to target completely on MapReduce. We are going to discuss on some generic algorithms which are going to help MapReduce to perform better. Fine. So design pattern is not only targeted on MapReduce. It just tries to tell you the solution of how much it can be done. Okay. So let's when we are finding out if a data or value we are searching existing or not, and why do I need to search it again? So Umesh, the point what we are trying to say, if you have a 20 billion records, okay, and can a filter can come back and say the record you are trying to filter may exist or may not exist, right? So we are going to provide a filter in between, so which is trained already to do the searching, which is smartly trained already to do the searching. Okay, so that's what we are trying to say. We are going to take a design pattern and we are going to train the design pattern across a particular data set, so that when you go across the actual record, you will be in a position to say this is fine or this is not fine. That's the actual thing. Yes, Vibhora, that will be enough. That will be good. Fine. And people, I am getting messages like I'm not able to hear audio, so you have to check webinar from your side for that. Okay. So yes, Umesh, we can see with the example. So that's what the example we are going to see, right? We'll see the example is going to explain it better. Fine. There is nothing it is different with combiners and recorders, etc. Shekhar. This is completely on taking a design pattern which is totally outside the scope of mapper and reducer. It's going to help the mapper and reducer in a different way. The combiner and reducers are again the concept of MapReduce only. Okay? Yeah. We'll sorting both the records so that filter will be efficient. Ravindra, as I said, I think we can see the example, right? I think we can see the example so that you can understand it better, how that filter records is going to happen, so that you will get a better picture on understanding what's going to happen. Okay, fine, Ravindra. Okay, on recordings of this, yes, everybody, you will get a recordings of this. We'll do this. Okay, so we'll see everybody for all the questions, and we'll see all the answers, because after the example you can understand the answers. Okay, so now. So as I said, who should know the MR design pattern? So basically, this design pattern is heavily targeted towards a Java developer and also for the MapReduce programmer. Basically, this requires MapReduce skills. Fine. As we already aware, I think today we can say blindly that there is a lot of people is already using MapReduce. Right. So that's why this has been targeted to the next level. How to make the MapReduce smartly and efficiently. So the design patterns in MapReduce can be broadly classified into these other things: summarization pattern, filtering, data organization, meta pattern, input and join. And as you already know, this is just a webinar session. We can't go in details. In the course, we'll be going in details of every single thing. So I will take one of the pattern, the filtering pattern, and I'm going to go over the use case of the filtering pattern so that you can basically understand how much smartly and how much efficiently it is going to work. Okay, so talking about the filtering pattern, so we are going to use a filtering pattern called as Bloom filter. So we are going to basically understand how the Bloom filter is going to work and how to apply the corresponding Bloom filter on top of your MapReduce design pattern. So Bloom filter is basically a space efficient probabilistic data structure. When we say a probabilistic data structure, it means that it is not going to guarantee you that 100% result. Yes, it is also going to give some negative results, but it is very much effectively can be used against the record data sets. So how we are going to define the filter, that much smartly it's going to work. So before even understanding the Bloom filter, so let me take a particular uh, example with an HTML file so that you can understand what the Bloom filter is going to try to do. Okay, so I'm going to basically take an example of the Bloom filter, whatever I'm showing in the diagram here. So this is basically taken from the courtesy of a website called as billmill.org. So this has been taken from that particular thing. So Bloom filters. So what it is basically trying to say is that it is going to work on a concept of hash algorithms. Okay. So what it means by the concept of hash algorithms. So let me go over the slide and come back to the example. So what basically Bloom filter says is that, so when you are going to work with the corresponding Bloom filter on the MapReduce design pattern, the process will be split into two things. One is basically three things. One is define the filter, next train the filter, then use the filter against the data set. So this is what we are going to do. So first we are going to define the filter, and next we are going to train the filter, next we are going to use the filter. So I will come to the define the filter. So first we'll understand how the filter is going to work. So let's consider if the Bloom filter is going to give a set of documents called as, or set of data called as mango, apple and grape. Fine. What it is trying to say, I can produce you three things. I can provide you three things. One is called as positive result, next is false positive, then is negative. Fine. So let's understand in the detail of how this is going to work. So basically what the Bloom filter says is, on a first stroke, define the filter. That's what we told, right? So let's define the filter. Here the filter size is defined as 10. So you can see totally a vector of 10 elements. Fine. And each and everything is basically whatever we are watching is the index of it. So next what's going to happen is that, let's say I am going to give something called as mango, something called as apple, or something called as grape. So what it is basically going to do is that it is going to use the hash functions. You can use any number of hash functions you want. Basically it is going to use the hash functions and it is going to set the bit for it. So how it does? So let's take that HTML example what I have. So let's see here. I'm trying to say I am going to use two hash functions here. One is called as murmur and another is called as f&b. You can use any hash functions you want, right? You can use basically any hash functions you want. The idea of the hash function is basically when you enter a particular string, it will convert that string into a particular hash key or index-based value. That's the intention. So let's say this Bloom filter is going to use two hash functions. One is called as f&b, one is called as murmur. So when I'm trying to enter a string called as hello, let's say I'm trying to enter a string called as hello, I'm trying to say add to Bloom filter. So what it does, basically it says for this hello, the hash keys have been generated in the index 0 and 6. Okay. So in this data set, it's remembering the hello has been populated with bits in 0 and 6. So next add another set of element called hi. So next again I'm calling something called hi. Fine. So now it says, okay, this particular person again given the bit of 0 and 30. So what are the string you are trying to enter, those corresponding indexes will be added and highlighted in this. So you can add any number of string. Let's add test. So it is going to create a hash key for that particular test and it's going to populate the corresponding indexes. Okay, 0 and 10. So now what happens basically is that there are three set of strings called as hello, I and test. For hello, it set the corresponding index and it populated the corresponding index. Okay, and for hi it has been taken, and for test also it was been taken. So this is basically the hashing algorithms concept used by murmur and f&b. Okay, this is totally, we don't need to worry about it. That's how they have been generated. This is an example has been taken out to show you basically how it works. How it is populated, you can go in detail of understanding how murmur works, how F1V works. You can use any hash algorithms you want, but here the concept is just to tell you how the Bloom filter is going to work. How they populated the index is depending on the hash function or the hash key algorithms which you are going to use. Here the algorithms has been used in murmur and F1V. So okay, so the murmur and F1V using with these two hash functions, what we have decided basically is hello I and test has been populated in the indexes of the corresponding Bloom filter data set. So now let's go and test. I am going to enter hello. Okay, when I'm going to say hello, Umesh Kaushik, as I said, this algorithm is just an example has been taken to populate the indexes. This is just an example to show you how the index is getting populated. The hashing function might work differently also, just to show you how the Blooming filter works here. Okay, yeah, just to understand what basically Blooming filter is trying to do in its indexes. So when I enter hello, yes, it says hello has been populated in the indexes. It says yes, it's available. When I say test, it says yes, it is available. Let's take another element called as fruit, something like this. It says no. Fine, because that has been not available in its corresponding data set. Fine. Just it's a string has been printed, Michael, there. It's just an HTML has been created to show you how it works. I have just given a string called as maybe instead of giving yes. It's just an HTML created from our side. Okay, fine, Michael. It's just an HTML string which I have given like maybe. So let's go back to this corresponding diagram. So basically the same thing what the Bloom filter base. That's see, one thing I want to tell you all is that this is just to explain you here how the Blooming filter is going to work. Whenever you give a particular string and mentioning the corresponding hash functions, it's going to populate the indexes for this corresponding hash index for this in its data set. Okay, fine. F1V and murmur are the hashing algorithm functions, Mamta, Java hashing functions, which is basically used, okay, which is available as a library file, not a user-defined functions. Fine, Mamta. Okay, so the same thing if you go back and look into this, so that's what basically is going to happen. So whenever you declare, I'm not getting for fruit, why it is resolved as no? Because the fruit indexes has not been available on that Vivek. When it's trying to create the hash key for fruit, it is trying to say the corresponding bit has not been populated on that. Fine. It is trying to, the hashing concept is a concept where it will convert the corresponding string into an hash key. When it's trying to convert it to an hash key, it populates the corresponding index as part of it. For example, for the word mango, it is using two hash functions and it is telling the corresponding hash functions are highlighting the bit 1 and 0 and 2. Similarly, for apple, the corresponding hash functions values are highlighted as in the bit 4 and 6. Similarly, for the word grape, it says the corresponding hash functions are coming in 6 and 8. Okay, so you can use any number of hash functions you want, but only one thing you have to make sure is that whatever the hash functions you are using, all the hash functions should return in the same result. Should return in the same result, like so hash function 1 and hash function 2 both has to say for mango we are going to populate in 0 and 2. Then only it will consider. Similarly for apple, okay, it has to say to having 4 and 6. Okay, the intention of having more than one hash function is to make sure, because one hash function may be better than another hash function in algorithmic approach, right? So that we just have to make sure is that we just have to make sure whatever it's happening. Okay, fine. So when you train this corresponding data sets, okay, when you train this corresponding data set, fine. So these are the set of things I have been trained. So I have trained only with mango, apple and grape. Mango, apple and grape says for the mango the indexes are 0 and 1. For the apple the indexes are 4 and 6. I request everybody to concentrate on the example, because all of your questions will be answered when you are going to concentrate on the example. Fine, everybody? Then we can take up the questions. That will be easy actually. Is it fine for everybody? I think you will understand all of your questions are what I'm going to explain is going to answer your all of your questions. That's what I'm trying to say. Okay, if you see this particular use case, you will actually all your questions will be answered automatically when the use case is what you're going to come up. Why fruit was not answered, etc. All those kind of things. Okay, so here you see what the point what we are trying to say is that a Bloom filter is going to train only against a particular data set. There are two things here. What are the two things? One is the real data, one is the trained data. So in this particular diagram, if you clearly see, the trained data is mango, apple and grape. I am only training with these three data. Mango says that the indexes is coming in 0 and 2. Apple says the index is coming in 4 and 6. Grape says again it's coming in 6 and 8. That's not a problem. They can collide, they can overwrite. But the only one thing we have to make sure is the Bloom filter is having an entry for mango, apple and grape in its corresponding vector. So once it having its corresponding vector, so what's going to happen? We are giving in the real time use case, we are taking mango. And it says mango is available because mango has been populated in this corresponding indexes. It says yes, mango is available. It says true positive. Then we are trying to give something called as fish. Okay. Unfortunately, the trained data set have been populated only in these indexes. Fish is not available in that particular index. So it says no. So let's say I am giving something called as banana. When you say banana, banana is coming up in the indexes 4 and 6. While training, I not trained with banana. I trained with apple and grape. Apple also ended up in 4 and 6. Fine. So you're trying to say that banana, unfortunately, banana is also having an entry in 4 and 6. So that is called false positive. It says if it's tried while decoding its corresponding index and those index are getting populated in its corresponding hash function, so it will say yes, it is available too. So that is called as false positive. So false positive is something which is it's trying to say even though in the trained data set this is not available or in the corresponding use case it is not available, but this particular person is trying to fall in that particular index which it has been trained. Okay, so if you see banana is going to see everybody, Vikash and Michael, this is just an example representation what is showing here, not the actual use case, right? We are just trying to say banana is falling in the indexes which it has been trained. The actual use case only will have the actual implementation. And use case, a representation here which is trying to tell you that banana is trying to fall in that particular index which has been already trained. So even though it is not part of the data set, it is just trying to say this is also falling under the false positive. So false positive is something, there are something in the data set which may not be existing in the actual trained vector. But since it is matching with the indexes, so it is going to come up and say it is available. So that is called as false positive rate. So we have to mention what is the false positive rate from our side. You can mention whether the false positive rate may be 20% or 30%, etc. It's up to you. You have to say how much false positive is acceptable. Fine. But the only biggest advantage here is if the Bloom filter says if the corresponding data is not there, it is definitely not there. So that is the biggest advantage of you. Okay, how banana is falling in the index. So calculating hash is overhead. So this is not an overhead performance issue and all because this is happening in the Hadoop MapReduce algorithm. Hadoop MapReduce is actually smarter in calculating the hashing concept. So that's not a problem at all. So it's going to be definitely faster. Fine. So we are going to train across a data set and those data sets is going to be filled in the indexes and the given string, if it's matching in the correct index, it says fine. Okay. So fine. So that's what basically happens. So here the banana is basically not part of the actual data set. The actual data set is having only mango, apple and grape. I have trained with only mango, apple and grape, but I am trying to give banana. Still it is trying to say banana is false positive because it is still falling in the indexes of mango, apple and grape. Okay. That's the reason only. I told check only for mango, apple and grape, but I'm trying to give banana, it's still trying to say it is available because it is falling under the indexes of mango, apple and grape. Okay, sure. Okay, for everybody, yes, the one as I said, right, the next is the actual implementation. Once we finish the complete implementation, I have to show the actual implementation. I'm going to show the actual implementation. Find the one. Yeah, fine. So one more thing, let's see how so basically when you see this, right, when you see this particular example which have been taken, there are only two things is going to happen. There are only two ways this Bloom filter can be represented. How the performance can be introduced much better. So if you are basically going to add more hash functions, it is going to provide a very good result. Fine. But at the same time, if you add more hash functions, it's going to get little bit slower. So there are only two things going to be possible here. Either you have to provide more hash functions. Okay. So as a Bloom filter, I am going to produce only two things. One is called as positive, one is called as false positive, one is called as negative, right? These are three things we are going to provide completely. A positive which says yes, data is available, and there is a false positive which says the data, yes, it's not there, but still we are telling up because it matches the index. It matches the index in vector. Fine. And a negative is something which is going to take care of, which is totally not there. So when you give a particular record, you are going to get all these three things. If when you get a particular data set and when you execute the actual use case, the Bloom filter will end up in these three results. It will say either in positive, it will say either in false positive, or it will say either in negative. That's the responsibility of taking Bloom filter. Okay, and the performance of this can be increased in two ways. One is either mention the hash function, more hash function, okay, or the false positive percentage. Two things are available to you. Fine. So if you mention the false positive percentage as more, so basically you are basically record which is coming up is not guaranteed is going to be existing or not existing. So with this, let's take a corresponding text. What if train set contains a million records and generation ask function for all those 4 degrees of performance? See, Devi, the train records should not contain the million records. Train set should be always a very minimum train set. Fine. So what's what Bloom filter is trying to say? If you provide more hash functions, it's always better. So you have to take a call. Either provide more hash functions or if you don't want more hash functions, if you're okay with an 50-50 result, then produce more false positive. So only these are two options, correct?